So today what we are doing is that we are continuing the discussion about defects in materials. Specifically, we are finishing the discussion about point defects. So what we will do today, I will just remind you what we learned last time. So last time we talked about intrinsic point types of defects in metals, as well as extrinsic type of defects that do exist in metals and how we treat them. So today we will expand this discussion and we will talk about ionic crystals. So these are typically the compound materials that have different types of atoms. So you know, for example, have a simple metal where you have identical atoms, and the question of the charge also becomes important. So we will see how you deal with these types of defects in ionic crystals. And let me just again emphasize the fact that these are technologically extremely important. We will see that, for example, the ionic crystals and the way how you, for example, dope semiconductors are really the basic of today's semiconducting industry. So we will learn that the doping and the way how you make contacts to transistors are really driven by some of the point defect densities and correlated or related properties. And on that note, one of the related properties that are related to point defects is diffusion. So we will learn that, for example, how one particular atom or different type of element interdiffuses into another is completely driven by the density, the starting density of defects in the starting material. So there is plenty of reading in Allen and Thomas, but for this particular subject, I would also recommend Callister, chapters 4, 5, and 7. And also I posted on Stellar Professor Taller's article. So Professor Harry Teller is a professor in Material Science and Engineering Department. He's one of the world leaders in the field of ceramic materials, and he wrote a really, really beautiful article that reviews point defects chemistry in ionic crystals. So if you're really interested in more details, this is a really nicely and accessible written article. So let me just remind you what we learned last time. So what we learned last time was very important. What we learned is that at a given finite temperature, there is a finite density of point defects in any type of a crystal. So there is no perfect crystal at a room temperature, any finite temperature. And the reason for that is the entropy of mixing. So what we learned last time is, for example, if you have a crystal, and if you have periodically arranged atoms within the crystal, if you, for example, want to form a vacancy, there is a certain energy that is required to remove that atom from the crystal. And that is the enthalpy of the formation for that particular defect, in this particular case, a vacancy. So if I want to remove, let's say, this atom here, there is a certain energy that is required by the system to simply take this atom and move it to the surface. So we are forming a vacancy. So again, I'm having these atoms here, and suddenly there is one missing atom here, and it has to emerge to the surface to form a vacancy. However, because we are changing the entropy, so the entropy is increasing by this particular function, so the fact that you have more sites for the atoms to occupy, the entropy of the system is increasing. So there is this balance between the energy that is required to remove an atom from the crystal and increased entropy that is happening during that process. So what we learned last time is that the entropy of mixing is really the driving force for the formation of the point defects in crystals, and how much of them you will have depends on the energy that is required to form them, on the enthalpy of the formation. So what we then learned is that you can quantify this, so you can say that the concentration of, let's say, vacancies or any types of defects, which is simply the number of the defects divided by the number of the defects plus the number of the atoms, which is approximately equal to the number of the vacancy normalized to the number of the atoms, because typically the density of these point defects is negligible compared to the concentration of the atoms, is an exponential function that depends on the enthalpy of the formation for that particular defect over kT. So what that means is that, again, the equilibrium concentration of point defects in a given crystal will depend on the enthalpy that is required, or the change in the energy that is required to form that defect, and it will be a strong function of temperature. So at higher temperature, there will be higher density of point defects. So this particular picture is very simple in metals. And again, you can predict whether vacancy or different types of point defects are more or less likely, depending on how much of energy is required for that. So today we will expand this discussion and we will see that the same principles hold for your ionic crystals. But before we do that, I would just like to remind you about different types of point and other types of defects that can in general exist in different types of crystals, because we will use some of these concepts today as well. So the first question is, this is a crystal, it's obviously imperfect, and there is a number of different types of point and other types of defects. And I'm asking you to recognize some of them. So can you point to the site in this image and just tell me what kind of defect that is? Anything that you can recognize? Yes?
Well, you have two examples of interstitial. Like the one lower center is self-interstitial, and the lower left is different type of interstitial.
So, okay, so this would be called self-interstitial. So this is an interstitial atom, but the atom itself is the same atom as the crystal itself. Okay, so we're also pointing out to this. What was the name for this interstitial?
It's also an interstitial, but I don't know the special.
Any suggestions? How would this be called? It is interstitial. It is. But it's called extrinsic. Okay. It simply means that the atom itself is different from the host crystal. Okay. Any other suggestions? Yes.
There is a substitutional atom on the upper right corner.
Okay. So this would be a substitutional atom. And for example, last time we learned a lot about, if you have a metal, we learned about the rules that govern how likely is that one particular atom will form a substitutional atom in a host crystal. And today we will also learn about how this is, what are the rules that govern these substitutional atoms exchanges in ionic crystals. Yes?
There's a vacancy like right in the middle.
There is a vacancy, that's right. Anything else? Yes. Yes.
I believe that's a dislocation on the left side.
Okay. It is a dislocation, so this is a line defect that we will learn about next time. But there is this extra plane of atoms that is reaching out this particular portion of the crystal. So it does exist above this point, but it doesn't exist below. So this is indeed a dislocation. Any other examples? Yes?
There's like a similar right across next to the substitutional atom.
Yeah, I think that you're right. So next to the substitutional atom. So for example, there would be something that you could call, right, here a dislocation as well, introduced in a different way. But there is this particular defect here. Do you know how this would be called? Yes?
How would that be a substitution cluster?
It's typically called a precipitate. So because locally the crystalline, so you can consider this to have completely different crystalline structure, or slightly different structure than the surrounding crystal. So this would be called a precipitate. If it was large enough, okay? So this is at the borderline between the cluster of substitutional atoms, and if that becomes large enough to form an entire small crystal, this would be called a precipitate, okay? Yes? Precipitate, that's right. So the reason I'm mentioning this is that, for example, when we talk about substitutional atoms, depending on the concentration of these substitutional atoms, you can form completely different phases in the materials and different precipitates, right? So the concentration of different defects will drive the structure